I can't really talk about some specific technique without giving you a background for why we're interested in this. So the subject is going to be frustrated spin systems, right? So when somebody says frustrated spin systems, what comes to mind? Triangular lattice. Okay, great. So let's start with the triangular lattice. I'm going to deviate from what's usually done and write down, so let me start with the Hamiltonian. So I'm actually not going to talk about Ising model at all, and I'm going to start from the very beginning with the Heisenberg model. So what do we know? What is the ground state of a Heisenberg model on a triangular lattice? So I know some of you know, but for those of you who are not experts on this topic, what are the ideas? So one way to think about this is whenever there is a doubt, let's see what happens in a classical system. So how do I define a classical model? So what makes these objects quantum? Is it just the hats that I put on top of them? So how do I delineate a classical Heisenberg model from a quantum classical model? What is the difference? All right, so I could have a superposition of states as my ground state. Very good. So if I say now I want to be classical, how do I do that? Exactly. So the way you think about this is that classically, there are several ways how you could think about this. You could think that S is just an ordinary vector of some magnitude, let's call it S naught, times a unit vector, that sits somewhere on a sphere, right? So this is Heisenberg model, therefore this is a sphere. Not to confuse with a block sphere, there is no quantum mechanics over here. You just have a vector n pointing somewhere, and this is a map, meaning that it starts from R, meaning let's say three-dimensional space, or in this case, triangular lattice. So I and J belong to triangular lattice, and it maps us onto the sphere, right? Now, it turns out that for simple lattices, so-called Bravais lattices, there is a famous theorem by Elliott-Leib. Elliott-Leib is one of the famous mathematical physicists, who I think back in 1970s. By the way, all of this, there will be detailed lecture notes that you will have after the lecture, so you may, or if you want, you can take your notes. If not, you'll have detailed notes later. And there I will put all the references. Okay, so I may get the year wrong right now, but they're all going to be documented. So what Elliott-Leib proven at the level of a theorem is that the ground state of a classical Bravais lattice is actually generally quite simple. It's a helical state. Now, helical means that if you look at this vector S as a function of R, generally it's going to look like S naught multiplied, let's say, by cosine of Q times R, plus some phase. And that's all there is to it. Now, S naught could be pointing somewhere, right? You could choose what this S naught is, right? And as was, you could choose your initial N, and afterwards it's a helix, right? So when you think of a helix, you think about something like this, and that's not far from the truth. That means that over here, maybe the spin is pointing up, and then it turns around, and then it does this, right? And so there is a repetition, and the period of the helix, call it lambda, would be proportional to something like pi over maybe 2 pi over q, where q is what's written over here, right? Now, how do we get q? It's too quiet, I can't quite hear. Say again? Boundary conditions? No, infinite system, no boundaries. Minimization, good. So minimization of what? Which quantity? Potential, very good. So so you're all very close to this. So look what's written over here. Jij, you could think of it as a function of Rij, the distance between them. Now the hint here is that we are talking about the Q vector. So what Leib suggested is that you do a Fourier transform, and you end up with a function J of Q. You plot it, and whenever this function has a minimum, that determines the value of capital Q at which this happens. So if you were to do this for a ferromagnet, which means so take all J's to be negative and let's say equal, right? What you will find is that this capital Q will be equal to 0, which means all the spins will be pointing in the same direction. So the period of a spiral is just 0, right? Or, well, unit length spacing. If you take Now, what happens if you take j's to be all equal between nearest neighbors, but antiferromagnetic, so positive? So this argument would tell you that the value of q you would get, this is 2 dimensions, remember, would be 2 pi over 3 in the units of 1 over a, where this is a lattice spacing. So this is actually easy to visualize. So if this is my triangular lattice, what will happen is that you will choose, let me see, that's not right. You will choose some vectors. Now let me see if we can get this right. So this will be pointing like that, and this would be pointing like, do I have another color? Oh yeah, this one. And this will be pointing like so. Well, that's not going to work. Let's be like so. And then they periodically repeat, which means this would be the blue one. And then over here I will have the, sorry, I have too many chalks in my hands. This would be red one, and then this would be yellow one, and so on and so forth, right? So you see that what actually happens is that you have what looks like a spiral, although it looks like a discrete, and it repeats after the 3 periods. So this would be the same blue arrow as pointing over here. Now, if you do a global transformation and you rotate all of the spins at the same time by an angle about 30 degrees from here, you'll get what people sometimes call a Mercedes state, right? Now, more conventionally, this is called a 120-degree state. So that is the fate of a classical Heisenberg model on a triangular lattice. Now the question now, what happens when we jump from a classical to a quantum world? So what makes quantum quantum? So one answer was that there was a quantum superposition. But how is it going to manifest itself here? Yes?
So like the components of these vectors are upgraded to non-Canadian operators, and they induce fluctuations that
Very good.
classical vectorization.
Very good. So one way to see it is that, so you write down the canonical commutation relationships. So for a given site I, if I have components alpha and beta, I apologize, then this would look like H multiplied by S, I, gamma, epsilon, alpha, beta, gamma. Well, this is the Levi-Civita symbol, right? And I'm missing the imaginary I that appears over here. Now, if you want to see how this works for arbitrary spin, it's useful to divide both sides by S squared. The logic being that if S grows, if I want to keep this quantity dimensionless and not dependent on the size of spin, I'll have something like this. And I'll here divide also by S squared. Now, if you think of what this means, the right-hand side goes roughly proportional like 1 over S. And that's why you see that the way you recover a classical limit is either by setting H bar to 0, that's one convenient trick, or by setting the size of the spin to infinity. Because that effectively makes it behave like a classical object, right? It's not immediately obvious why that should be, because if I have a spin of a size S, quantum mechanically I have 2S plus 1 states. And so therefore, if I have a system of L sides, my Hilbert space is actually going to be 2S plus 1 to the power L. And so you would think that if I make spin S larger, I should get more in trouble than less in trouble, but it turns out that actually large spin is your friend. So for a long time, one of the ways of dealing with the problem was to start essentially with a classical regime, which is what Elliott Leib told us to do, and then consider small fluctuations in the quantity which is 1 over the size of the spin. This is what Jean-Noël alluded to earlier today when he talked about the smooth fluctuations, right? This was a number 3 on his list of what to do if you want to solve a quantum problem. So number 3 was to find what are the collective excitations in that of the smooth variable. In the case of the quantum spins, this is often referred to as a spin waves, okay? And so the spin waves, you could think of it, is of order 1 over S, or maybe higher orders, if you're willing to go higher, expansion, which becomes more and more accurate the larger the size of the spin. Now, today we're not going to talk about the spin waves. Instead, we're going to jump to the case of what's often of most interest is the case where spin is equal to 1/2. Now 1/2 is demonstratively not large, not in the sense, right, 1 over s, in that case is 2, is not a small number. And so you may rightly think that therefore any attempt to do something like this is bound to fail, right? So people actually try to do 1 over s correction for the case of the triangular lattice. And what you find if you did this, and this dates back to 1990s, and people like Jolicoeur, Andrei Chubukov, Elbio Dagotto, they've done a bunch of studies, you will find references as my notes, where essentially what they find is that first of all, if you just assume that there is a nearest neighbor coupling, perhaps surprisingly, you actually recover that there is the same 120-degree state as you would expect. Now, the idea to try to induce further frustrations in the system is to say, well, how can I frustrate the system? Well, remember, I started with something very basic. I said, let's make all j's to be positive and same. So let's make them not just 1, which let's call them j1, but let's introduce the next nearest neighbor interaction, which means I want this to spin stock to each other and maybe this to spin stock to each other, and we're going to call this interactions j2, right? So if you did this, then this is the subject of j1, j2, so-called nearest and next nearest neighbor Heisenberg model on a triangular lattice. And what you might imagine is what would happen if you increase the value of j2, right? Now, if j2 is 0, let's start from here, you end up with the 120-degree state. Right? Now, what exactly does that mean? Does it mean I'm allowed to draw a picture like I did here and say this is the ground state of a quantum system? So why not? So you may or may not have heard this, right, either in undergrad or graduate education. But let's say I take even a simple example. Take a square lattice. We all heard about Néel state, right? And so often in the textbooks, the Néel state is drawn like this. The question you should ask yourself is, let's say I take that to be the eigenstate, to be the ground state of my system. So I literally take a product states. This spins points in this direction. This is here. This is there. This is there. Right? So for instance, if there are just 4 spins, you could write the wave function literally as the product of, let's call this direction, let's quantize this and call this the z direction so I don't have to deal with the Euler angles. And then just call that the first spin, let's number them, 1, 2, 3, 4, that the first spin is pointing down, the second spin is pointing up. So this is first, second, the third one is pointing down, and the fourth one is pointing up. This is a so-called product state. Why product? Because you see that the Hilbert space essentially becomes separable. Wrong terminology. It becomes decoupled in a sense that the wave function is just a product of the wave functions of individual spins, right? Yes, this is a spin half object, so this object lives on a Bloch sphere, this object lives on a Bloch sphere, and so on and so forth. Now, what's wrong with that state? Why is that not a solution? Yes? It's not an eigenstate. How can I see that? Very good. So I'll try to see if I can amplify that. So the answer was that if you write this in terms of raising and lowering operators, you will manifestly see that that fails. So I want to have a poll of hands. So raise your hands, please, if you understand the argument as being stated. Okay. So maybe about half, maybe 1/3 of the audience. So let me see if I could rephrase what's being said. If I write down Si as J, I could write this down as a product of obviously SZ plus SX plus SY, right? Now let's leave this independent, meaning let's leave this alone. This actually is a perfect, so the state that I've written is a perfect eigenstate of this operator, right? Because when Siz acts on this state, it just gives me 8 minus h bar plus h bar minus h bar plus h bar. Voila, it's an eigenstate, right? Now this one, this is an identity. You could write this down as 1/2. Take the first spin and raise the operator. The second one lower, plus Hermitian conjugate. So what does it mean? I have to take this first spin. So let's see what happens if I take, this state. And let's say I consider just the first and the second spin. Let's forget about the 3 and 4, right? So if I were to write down S1 plus S2 minus, let's not worry about Hermitian conjugation yet, and act on the state psi, you will see what's going to happen. The first spin is going to flip, the second spin is going to flip, and I end up with something looking like this, which is obviously not the state I started from. Yes? So often this is termed quantum fluctuations. The terms of this type, which involve the raising and lowering operators, are manifestly non-classical. Right? It's something that flips the spin, and now you have to know what are the allowed quantum states of that object. And so that's why dealing with the quantum systems of spins is hugely complicated. Now, in this lecture, we're going to talk about one of the ways that was found to be perhaps the most promising in dealing with the systems, at least in 1 and 2 spatial dimensions. And that goes by the name of the density matrix renormalization group, right? So we'll talk about why density matrix in a moment, but let's first focus on the last 2 words of this, renormalization group. So when I say renormalization, what does that tell you? I mean, obviously there are graduate courses that can take an entire semesters that are just talking about the RG. But what's the basic idea of it, if you were to phrase it in 1 or 2 sentences? Very good. Coarse grain. Very good. So the first statement is often inferred when people talk about the K space RG, or the reciprocal space RG, because there, when you talk about the powers of K, right, so K being the momentum, right, that has, so let's say K squared, has the meaning of energy, well, K squared over 2m, right? And so you could see that when we talk about high energy state and integrating them out, that naturally tells you, okay, well, integrate out the high values of K and you're only left with the low ones, and that's what you want, right? Now, the second statement of this is a slightly different variety. It says something about coarse graining. Now, what does it mean? Takes the first and the second, and then throw away the third, and then coarse grain. So the coarse graining actually comes from the so-called real space RG, which in some sense predates that statement about integrating out higher degrees of freedom. And the idea of it is based on a real space formulation. One of the creators of this was Leo Kadanoff, and there were many others who were working around the same time. I'll erase this part. So what the real space RG amounts to, and I'll focus on this because it's a precursor of the method that we're about to discuss, is the following idea. Imagine, so we're going to start with 1 dimension because it's A, it's easier for me to draw. B, it's easier actually to do it numerically. So let's start with 1D. So let's say I have a bunch of systems, not a triangle lattice, but a chain of spins. And they may have nearest neighbors or next nearest neighbor interactions. For now, let's just say nearest neighbors for simplicity, right? One way to formulate NRG is the following way. You start with a system and you partition it into blocks. Right? And let's say each of your blocks has a certain L number of spins, right? And let's say you choose your blocks not too large, so you could actually diagonalize the system exactly. Now, what is the size of the Hilbert space that I need to deal with over here for spin half? Right, it's 2 to the power L, right? Because each Heisenberg spin 1/2 gives me a power, the Hilbert space is dimension 2, right? Pauli matrices, as you know, are the operators that act on the spin. So if I want to deal with L spins, I need to deal with matrices of dimensions 2 to the power L. That's why exact diagonalization for spin half is limited to about 32, maybe 34 sides. Am I correct, Thomas? Well, right, if you use additional symmetries to simplify this. But the state of the art is roughly roughly there, right? Even storing the wave function of, let's say, 40 spins is out of the question. By the way, do you know how big is this number? So let's say you had 300 spins. This is something often that I give a quiz to undergrads. How big is that? Oh, very good. Yeah. So that's, so if you, yeah, so it's roughly this, it's roughly that, right? Now, why that number is significant, I just pulled it out. I mean, this 300 is not essential, but why this number is significant is because this is roughly believed to be the number of hadrons in the visible universe. So if you had a classical computer and you wanted to model 300 spins 1/2, right, a chain, let's say, just to store that wave function, you would have to, you know, assuming you had a single bit, a single classical bit associated with each hadron, which is means, you know, proton and neutron in the universe, you would run out of space. Okay, that's how vast this exponential growth is. Okay, so let's choose L, obviously not this, and let's say smaller than 30. Let's choose it to be 5, like I drew, something like that. Now, what you do next is that you say, great, I solve this system exactly, right? And I end up with 2 to the power L eigenstates, right? I diagonalize the Hamiltonian, so by definition, once I diagonalize, my Hamiltonian becomes a matrix that has energies and so on, all the way to n that's equal to 2 to the power L. Now, the idea of the coarse graining that was phrased is that what you want to do then is to somehow enlarge this to cover the entire system. So one way to do this is at the next step to try to take 2 of these blocks and join them together and say, right, now I want to diagonalize that system. Now, doubling the system size is not a good idea if you just want to do exact diagonalization. But what you could use is the fact that the first block is just as exactly the same as the second block. So you don't need to diagonalize it twice. You just diagonalize it once, which is what we've done. But you can't possibly deal with the matrices of the size 2 to the power twice L, which is what would be necessary if you were to do it brute force. So instead, you're forced to cut off somewhere and take the lowest, I'll use a small m as the number, and use the small m number of states as your cutoff. And then once you're done, what you're going to do is that you're going to take the Hilbert space, which is going to consist of this m states, times another block that has exactly the same matrix. So what ends up happening is that now, instead of 2 to the power 2L, you've simplified your system that it has m times m states, where you've deliberately chosen m much smaller than 2 to the power L. So to give you a specific idea, maybe you want to choose m to be of the order of 1,000. Okay, if you want to push it, you could choose it to be a couple of thousands or 10,000s, but that's the idea. Something that's manageable. Now, what's the idea is because you're trying to capture the lowest lying states, you've chosen m of those, let's say a couple of thousands, right? Now we are talking about the matrix, which is 1,000 by 1,000, which is 1,000,000. So what do? Well, you diagonalize that, but you only keep the lowest m states again. And so now, after you've diagonalized this, this has become your block. Now, guess what? Now there is another block just like that, and you take this, and you multiply it again by 2. And then what you see is that you could start from this as thinking that you're starting from the microscopic zoom-in scale. I've started with 5 sides. And eventually this grows exponentially to become very large, right? But each time you do this at the cost of discarding some number of states, right? So this dot, dot, dot that stays here are the states that I've discarded. Now, as formulated, what I've just told you is so-called numerical renormalization group. And it was first invented by Ken Wilson in the early 1970s. He was applying it to a one-dimensional problem, which was actually a result of a map from something known as the Kondo problem. For the sake of the brevity, and because this is not central to today's discussion, I'm not going to tell you what the Kondo problem is. You know, somebody like Professor Coleman has spent half of his lifetime studying that problem. He can tell you in more details than I can about what that problem is. But it turns out that the Kondo problem for a single impurity could be mapped onto a semi-infinite chain, which means, okay, so there's one side which is special, let's call it side 0, and then the chain just goes to infinity. And then what Wilson did was essentially applying this technique, except instead of growing it in both directions, you start from side 0 and you keep growing that way. And that's the essence of NRG. Now, the reason, or part of the reason why Ken Wilson got the Nobel Prize was because the Kondo problem has not been solved. It took a further 7 or 8 years before an exact solution was actually found using the beta ansatz, but that's a different story. But the point is that that was a major breakthrough. The problem that withstood some 40 years of onslaught was solved. Well, that's from when it was first experimentally found. It was finally solved using a numerical argument, right? Now, what ends up happening is that if you start with something like a model that I've just given you for the Heisenberg spins, and you say, great, Kent Wilson got a Nobel Prize for it. Let's do it, right? I take one-dimensional chain, let's say nearest neighbors only, you give me the value of j, we start this procedure. People tried shortly after Wilson, within the span of maybe 10 years, and found the results were very, very discouraging. So what happened is that if you do the procedure the way I described, and you keep M of about 1,000 states, what they're actually trying to do was solve a one-dimensional Heisenberg model, one-dimensional Hubbard model rather than Heisenberg model. Part of the reason is that, well, for aesthetic reasons perhaps, but the solution of 1D Hubbard model is actually exactly solvable using beta ansatz. So there was a benchmark that you could look at your solution and compare it to an exactly known result. And what they found is that you got an error of NRG, which if you use this number of cutoff, which was about 10%, for a system whose size they were trying to solve, right, for L, which was somewhere between 16 and 30 sites. Now remember, this is a Hubbard model, so in the phase space of the Hubbard model, the Hilbert space is not 2, but 4, because you could have not only up and down, you could have empty sites, and you could have doubly occupied sites. So we are talking about the Hilbert spaces that if you try to do it brute force would be 4 to the power 16 or 4 to the power 30. Okay, now with the modern methods, you could try to tackle 4 to the power 16, but definitely not more than that. Right, so this is just to give us the same ballpark. Now, they found huge error bars, way worse than what Kent Wilson did for the Kondo problem, where it was basically down to numerical precision. What was the problem? The problem was not evident, and it took a long time to actually find out what the problem was. So Kent Wilson's solution for the Kondo problem dates back to early 70s. It took nearly 20 years, and it was in 1992 that Steve White, who's now at the University of California, Irvine, who came up with an improvement. And the improvement now goes by the name of the density matrix renormalization group. Now, in order to understand what exactly Steve White did, let us first understand why NRG fails. Because if you understand why that fails, we can try to see what was the line of thought that Steve White had. And the reason it fails fundamentally is because when each time you take a block and you diagonalize it, you take that block completely in isolation from the rest of the system. So what you're forgetting is that that block has sort of dangling bonds on the left and on the right, by which it's coupled to other systems, to the rest of the system. The reason why NRG works so marvelously for the Kondo problem, it turns out because of the special way in which the Kondo chain is set up, the strength of the links decays exponentially as you go down the chain, right? And don't ask me why, this is part of the NRG solution for the Kondo problem and the way the mapping is done. But believe me that the actual coupling constant J isn't constant, it's actually decaying exponentially. Which then explains why by the time you reach the 20th side, it's basically the same as thermodynamic limit, right? Now here, it's far from being true because all the links have the same strength. So one way to formulate DMRG in one sentence is that DMRG works by diagonalizing blocks not in isolation, but take into account their environment. So for instance, one way, I'll talk about the specific algorithm later, but one way how you could explain this is in the following way. You could start by essentially creating a block, and so far it's similar to what I've told you, and then say, right, but I shouldn't really try to solve that block by itself. We know that's ill-fated if I just do this. Instead, what I'm trying to do is to incorporate the fact that it's coupled to a bunch of sides over here. So let's call this part of the system A, and whatever's left is B. Now I still want to take this whole thing and cut it out from the entire system and make that system manageable in size, right? So I don't want the B to be the entire infinite chain. I want it to be something of the kind that I just drew on the board, right? So it's I can try to search for a solution. Well, now what? The way I drew it, right, it still would suggest that either you have to solve the entire block A plus B, or you solve A separately, you solve B separately. How's that different from what I've been trying to do here, right? And the key insight of Steve White was that the problem lay, crucially, at this cutoff step. The problem lay in the statement that what I should do is to keep the lowest m eigenstates of the problem. Now, why does it make sense to keep the lowest m states? Well, it's an essence of RG. It's what one of the answers that came out from the audience was that, look, it's to decimate the energy scales, get rid of the higher ones, keep the lowest ones, right? So it seems to be very logical, except it doesn't work. Now, why it doesn't is because, so one way how Steve White argued is that imagine you start with a particle in a box, right? And let's say, so hard box, right? So which means infinite boundary conditions. You know what the ground state is. It's going to look somewhat like this, right? Now let's say you can't solve, let's forget about the fact that we can solve this exactly, right? Let's say it was some unknown problem and somebody's trying to do it brute force on a computer. And let's say they cannot quite go from a system size L. So instead they choose a smaller system of size little l, that's my block. And then they say, okay, let's just try to solve it. What will you find? Well, you will find that the ground state of this wave function, right, if this is your block, has to vanish at the boundary points because of the infinite boundary conditions, which means you're going to end up with the wave function that's going to look maybe like this. So let's say you normalize them properly, you compare the two, and you see that they look nothing alike. So no matter of trying to splice blocks like this, right, is going to bring you to what you actually want. So instead, the idea was, well, maybe I shouldn't keep the ground state. Maybe I should keep other states of that box. And the first clue was to trying to play with the boundary conditions, actually. So instead of saying that this block should have, infinite boundary conditions, let's make them periodic, or maybe anti-periodic, or maybe make them open. Why? Because what you're trying to do is to mimic this part of the wave function that looks like this, not the one that vanishes at the two ends of the block, right? Now, the understanding came from the fact that what you should do is to focus on this block over here, and this is my system A, and then think of the rest of it as, as the rest of the system B. And this is the kind of problem that in quantum mechanics goes back to the works of von Neumann and later Feynman, and it's what we know when we talk about mixed states. The statement that you cannot describe the block A by writing down its wave function. Why? Because even if you assume that the entire system is a closed system and you know the ground state wave function for this state, you can't write down a wave function for the isolation. For the subsystem A in isolation, you have to deal with what's known as a density matrix, right? Formally, it comes from the following. What you should do is to, so first of all, what is a density matrix, right? Formally, it's a projector operator of this kind. If it was a pure state defined on the entire system, so this is defined on system A plus B, then this is what the density matrix would be. Now, the reduced density matrix is something that tells you not about the property of an entire system, but only of the part A. How do you do this? You define rho, I'll put a little a as a superscript, by tracing out the B, the environment, of the rho of this A plus B that's written over here, right? Now, you will end up with obviously less amount of information because you're now trying to describe something that has Hilbert space that's smaller, right? And the price you pay is by truncating out chunk of the system. This is no longer a ground state, but in fact what ends up happening is that generally this is going to be of the form where there will be some sum over a WA multiplied by, I'll use phi, right? So you could write this like this, where phi was a, actually let me use little a, that's going to be a better. So I'm going to use Dirac-Braquet notation and write this down like this, where a is some eigenstate of the system A taken with some weights WA. So what does it mean? If I ask, so if a person comes in now in the door, right, and we ask them, well, with what probability is it going to be a man or a woman? Well, we don't know what the answer is, depends on our heat bath, right? But let's say if a person were to come in, you wouldn't say, well, it's a quantum superposition of 30% of it's being a woman and 70% of it's being a man, right? Makes no sense classically, and it doesn't make sense here. So what you should think of this as classical probabilities. Because they're classical probabilities, the sum of all WAs better be equal to 1, which is another way of saying that this should be a unit trace matrix. Okay? I'm saying probably that's something that's evident, or maybe you've seen this before, and then I apologize if that's the case. But that's the basics of the density matrices. Now, coming back to our chain, what Steve White had in mind is that instead of keeping the m lowest eigenstates, which seems intuitive except it doesn't work, he said, well, let's keep the m most probable eigenstates. So if a person walking in has a 90% being a man, I don't care how short they are, right? I don't care about their height. So I'm using, obviously, some not very clever analogy, but what I'm trying to say is that the eigenvalues, the energy eigenvalues of the states are totally irrelevant if those m states are the most probable for the system that I'm trying to describe. And so the recipe works as follows. You start from a block A, you form what Steve White called a superblock, which is you attach a part of the system that works as a heat bath. You solve, you make sure it's not too large so you can actually solve it. You find the density matrix for the entire system A plus B. You trace out B, you end up finally with something that just describes the system A. Now clearly you've done more work than you wanted to. You haven't just diagonalized A, right? But you gain something in the process, because what you found are not just what are the lowest m eigenstates, but what are the most probable given how strongly system A coupled to subsystem B, right? Now, you could view now numerical RG, the one that Winsel invented, as a partial case of this one, if the coupling of B to A is sufficiently small. Now, why is that? Imagine that there are many, many sides, and I take size of the system B go to thermodynamic limit. Assuming the system is ergodic, that would mean that the subsystem B would act as a heat bath for the subsystem A. Now, what does it mean to have a heat bath? It means it's some chaotic system that has something that we could refer to as temperature, right? Now, what that means is that now I have a system, subsystem A, at temperature T. How do I write down the density matrix for such a problem? It's a Gibbs distribution, right? So if you give me a set of eigenenergies of the system A, I know what the probability is. The probability of finding a given state is proportional to exponential of minus beta, the eigenenergy of that system, where beta is the inverse temperature, right? But that's known as a thermal density matrix. It's a fancy way of saying that the Gibbs distribution formulated in the words of density matrices just tells you that the density matrix rho of the system A would look like an exponential of minus beta h, where this is the Hamiltonian of the system A, right? Think of left-hand side and the right-hand side as a matrix. If this matrix is diagonal, then I could just exponentiate the eigenvalues, and this is what I get from the left-hand side, right? Okay, so formally this is a solution. And now watch what happens. If I were to keep the m most probable eigenstates of the system, well, which ones I'm going to choose? The ones that have the lowest energy, because for them, WA is the largest, right? And so essentially NRG works, and obviously DMRG will too, whenever this roughly obeys the thermal distribution. Whenever it's way out of the whack and strongly coupled to the rest of the system, you can't make such an analogy. You can't just say that, oh, it's a heat bath that has effective temperature, and that's why NRG does not work. DMRG does not care, because what it does, it chooses m highest eigenvalues, not of the energies, but of the density matrix, right? It chooses the highest m values of these W's and throws away the rest. In DMRG jargon, whatever you throw, the rest is called truncation error. remember, all of them sum up to 1. So what you actually throw away, so, you know, basically the sum over a smaller than m, which is what you keep, right, plus the sum over m larger or equal to m is equal to 1. So if you've kept this, whatever you throw away is a number of order 1, well, between 0 and 1, that tells you about how much of it you're actually throwing away. And the remarkable thing about DMRG is that it works. It works remarkably well in the following sense. If you take a one-dimensional system like a Heisenberg chain I've just introduced, and you actually make the DMRG algorithm, you will find that keeping as few as 100 states, you could get up to the 9th decimal digit, basically machine precision, in the energies of the ground state of the infinite chain. Well, actually, what I just stated is not quite right. Yeah, that's right. So let's say we're dealing with infinite system size, or the system of sufficiently long size, right? Now, let's talk a little bit about how you would actually implement this. Obviously, I'm not going to write code in front of you, but what we're going to do is to try to conceptually, just like I tried to use NRG, let's see what you will actually find. So the idea would be roughly as follows. All DMRG more or less works in 2 steps, right? So there is a first part of it, which is called a warm-up. And in a warm-up, what you usually want to do, so what I'm going to describe in what follows is the so-called finite DMRG. So let's say you want to study a finite system of 100 sites, right? I hope I've already convinced you this is hopeless task to do it brute force, to try to solve a system of 100 spin 1/2. So how are we going to do it? The idea of the warm-up is that you start with a system. This is my block A, and I'm going to add to it just one site. That's going to be my bath. In different implementations, you could have more sites, but typically people just add one site. Okay. Now what you do next is that you say, right, I'm going to take this subsystem A, right, and I'm going to form a super block. So this is my A plus B. I'm going to solve this problem, right? Now what I'm going to do, the subsystem A, let's has L sites. So the total number of blocks is just 2L times 2 for subsystem 2, right? So now once I solve this and I found all the energy eigenvalues and eigenvectors, I know the density matrix. I integrate out the part B, I end up with a reduced density matrix, which by definition has 2 to the power L eigenvalues. I'm not going to keep all of them. I'm going to take this, omega A's, right, where the sum goes from 1 to the 2 to the power L, and I'm going to keep the first m of them, right? And I'm going to keep those first m, and the rest is the truncation error, okay? So that's the idea. Now, once I've done this, I'm going to say, right, but I want to do it somehow symmetrically. So why don't I do the same on the right-hand side of the system? I'll select a bunch of sites. This is going to be my subsystem A. There's going to be a chunk sticking out, and this is going to be my B, right? And so now that you've done this, you found the m lowest eigenvalues for a given system size. This first part is done. Now you have to do the hard part, which is to renormalize all the operators. So for the sake of brevity, I'm not going to go into details, but if you imagine defining a spin operator, or as z or as x, whichever you'd like, on the system, you now want to make sure that if you enlarge the system from L to L plus 1, now you have to deal with the matrices that has bigger number of sites, and you have to project onto those m lowest eigenvalues that you're eigenvectors that you're actually dealing with, right? So as a result of this projection, you end up with an effective description of the system that is now somehow truncated down to this m sites. At that point, you stop and say, great, I'm going to call this whole block, which before was a super block, I'm going to call this my A. So what you're going to do at the next step is to take this whole thing and add to it one more site. And you're going to do the same on the right-hand side. You're going to take this entire system and you're going to introduce another side on the left of it. And you're going to proceed. So what you do is that each time you do it, you grow the chain by 2 sides, right? So if I started from here of L plus 1 plus L plus 1, now each of these blocks is L plus 1, except I've truncated it down to this effective description, and I added one more side, right? And I keep going until I reach the lengths that I wish. So let's say for for simplicity, that my chain has even number of sides. Otherwise, you have to do some tricks. But let's say you have even number of sides. So let's say 100. Well, great. I start with 5. I repeat this procedure by about 20 times, and eventually I end up, well, more than 20, about 40 times. And eventually I end up with 50 on the left and 50 on the right. Make sense? That's a warm-up part of the DMRG. Now, that by itself already gives you actually quite a good precision. So in fact, there are some algorithms, sometimes going by the name of infinite DMRG, where with some tricks, this is all that's being done. But typically and traditionally, the way Steve White formulated DMRG, there was a second step, which is often described as sweeps or sweeping. Now, what does it mean? So the idea was to improve the accuracy. You see, I've started with the system of 5 sides, and eventually I added 1, and I kept going, and eventually I end up with this description of my system, right? But where is the guarantee that in the process of, keeping the M lowest states, I haven't missed something? The idea that Steve White says, okay, let's take what I ended up with, which is this. So now I have a system. Let's say, so actually what the sweeps are introduced as an intermediate step between here and here. That's where the sweepers come in, right? So before you declare that you're done and you've grown your system by one side, you do something extra. What is this extra? It amounts to basically the following procedure. So I already called this L+1. So let's say my super block, I'm just call it capital N, which has, in this example, L+1 side, okay? I start from this, and I have another block of size N. That's before I reach this part. What you do is that you say, great, but what, as written, this is equipartition, where the left-hand side of the system is the same as right-hand side. But who told me that I always have to choose the environment to be as big as the system itself? What if instead I thought about this whole system as consisting, as consisting of, let's say, 2 sides on the left-hand side, or generally, some minimal number of sides, let's say 3, and the rest of them, which would be 2n minus 3, and this is 3, would be the environment, right? So remember, typically you do this for the system that you can still deal with numerically. So what Steve White would suggest you do is that you take this system, it's small enough that you could diagonalize completely, but actually you don't need to do diagonalization because you've done it at some point when you were building this object, when you were doing the warm-up. You typically already have a solution for, let's say, 3 sides, when this was only 3 sides long. So you already have a density matrix that describes a system A, and now you have the rest of the system on the right-hand side, which is described by some density matrix B. And what you do is that you repeat this procedure where you keep the M lowest eigenvalues, but you do it multiple times, where in each subsequent iteration you enlarge the size of system A by 1, and you decrease the size of system B accordingly. So now this is going to be 4, and this is going to be twice n minus 4, and so on and so forth. So what happens is that you could think of it as a boundary separating subsystem A and B, constantly moving to the right at each iteration of the sweep. So the sweep is declared complete when that boundary moved all the way to the right, bounced back, so to speak, and went all the way back to the initial position that you started from, right? So think of a sweep as something, well, maybe the Turing machine analogy would work here, but it's something where there is some clever algorithm which basically refines and reshuffles the M lowest eigenstate of your system to make sure that all environment can maximally entangle with your chosen system. And because you don't know how to choose A and B, well, let's cover all possible choices, right, that we can have. Now, the actual details of implementing the algorithm of DMRG could be challenging, and obviously the goal here is not to cover them. What I'm trying to do is to give you a conceptual picture of how DMRG works. Let us now ask ourselves why it works. So it's all good and well to have the insight that Steve White had, but it's still a major miracle that it actually works as well as it does. So there are cases where DMRG fails. And so let's try to understand where it works, and by knowing where it works, we'll hopefully also understand where it fails. Now, at the heart of the DMRG, there is a concept of entanglement, the entanglement between the subsystem A and the subsystem B. Right. Now, one way how you could think about what we are trying to do here is to formulate this in terms of the so-called entanglement entropy. So who of you have heard the words entanglement entropy? Right. How many of you, if I ask you to come to the board, could write down the expression for it? All right. So there's nothing wrong, by the way, with this. You don't have to memorize and know by heart what the von Neumann formula is, but let's see if you can recover this. So if I have, do you remember what equation is on the tomb of Wolfgang Boltzmann?
Oh, yeah.
So the entropy is what? K times W. Now what is W? Yes, very good. You see, you keep me on track. Okay. So K, well, nowadays we would put little b. I mean, Boltzmann obviously didn't do that, but this is what we know as Boltzmann constant. But what is a W? It's a number of microstates that describe a given macrostate. Right, great. So now we're not going to go too much in thermodynamics, but let's try to think in terms of the system that we have, right? What tells me about how many microstates that you have in the system? Well, obviously it has something to do with the size of the Hilbert space. The more states, the more freedom I have in this. But ultimately, it turns out that you could rewrite this in terms of the density matrix, right? So von Neumann wrote this as minus, well, I'll do a trace. It's minus, we'll keep the KB, trace of density matrix times log with base 2 of the density matrix. Now let's see how this would work. So the simplest case you could say is that, okay, let's say our system has dimension D, right? So this is the dimension of Hilbert space. Now let's say that our system is at infinite temperature. So what does it mean, infinite temperature? So in my example, beta is 0, which means all eigenstates are equally probable, right? So what does it mean? That all my WAs are actually identical, and they're 1 over D. Why? Because when I sum over all over A, WA, remember it has to be unit trace, right? And A goes from 1 to capital D. So let's plug this into this formula. I'm summing, so trace just means a summation. Let's say it's a diagonal matrix. I'm summing 1 over D log of 1 over D. Well, I'm just summing the same number D times. So what do I get? I get the entropy, which is just D times 1 over D log of 1 over D with a minus sign, and let me introduce the Boltzmann constant over here, right? Now you see what ends up happening is that, okay, well, this just cancels out. I end up with minus Boltzmann constants times log of D. What is D? Is a number of microstates, right? It's the entire Hilbert space that describes my infinite temperature state, right? Now you could show that the same works if you were to start, for instance, with thermal distribution. If you started with the Gibbs and you plugged it in here, you will recover the laws of thermodynamics from this stat-mac argument, right? Okay. Now, if ρ is the density matrix not of the entire system, but the reduced density matrix, the one defined here, right? If I put here A and I put here A, what this object describes is a relative entropy of subsystem A relative to subsystem B. Or another way to say it is an entanglement entropy. How entangled is subsystem A with subsystem B? Okay? Now, let's see where this leads us. Imagine that you have a fixed. So imagine that somebody gave you the entanglement entropy, its numerical value, for a given system, let's say for Heisenberg model. The question becomes, how efficient can I describe that system with DMRG? What I'm trying to establish is the link between the truncation procedure, where I'm keeping certain number of states, M, and the fact how, the entanglement entropy. The idea is as follows. Basically, I am allowed to throw away the truncation arrow, to throw away those states, provided this W's decay sufficiently fast with the index, right? Now, how do we know how fast they decay? Well, it turns out that some of this information is already encoded in here. For instance, if they don't decay at all, if they all have the same value, then as we just saw, you get the maximal entropy, right? This is a purely, it's a completely mixed state. So the idea, it's really back of the envelope calculation, is as follows. Let's pretend that all my W's are equivalued. It's never the case, but let's just pretend that all of my WA describe my entire state. And let's say I'm gonna choose this, where D is the number of states I keep. Actually, let me use M, not to confuse you. So it's not the full size of Hilbert space, it's the number of states that I kept, right? If I were to go through the argument that I just gave you, what you will find is that the entropy, right, the entanglement entropy of A with B should be by this logic given by log M. Well, log at the base of 2, actually, right? So now, if somebody told you that that entanglement entropy is given to you, you could back out from this how many states you would need to keep, right? Because if I want to describe this object, whatever this is, right, 20, and what this tells you is that, therefore, the number of stands I need to keep would be 2 to the power s. Voila, this is very, very brush stroke, back of the envelope argument telling you how many states you should keep. Now, why is this important? Is because a lot is known about one-dimensional systems. We actually know how this entropy S scales with the system size. And believe it or not, it's because of the black holes that we know that. It goes back to 1973. No, this is not a joke. So in 1973, a bright Jewish physicist who was working at Princeton at the Institute of Advanced Studies, his name was Bekenstein, came up with an idea that black holes had entropy and therefore temperature. And as you probably know, the black holes are these very interesting objects of which you can't really speak, of their volume, but you can have a well-defined surface area defined, let's say, by the Schwarzschild radius or otherwise by the event horizon, right? So if you take the area of the event horizon, it turns out that the entropy of the black hole goes proportional to the surface of that object. This goes by the name of the area law. So what this tells you is that if I am in a certain number of dimensions, and I have a system of size L, right, and let's say dimensionality of the system is D, then the entropy of a certain, if the area law is obeyed, the statement is it goes not as a volume, not an extensive quantity, but it goes as the 1 power less the dimension of the system. And it turns out that for the ground states of short-ranged Hamiltonians, so this is a deep statement which only came to the fore in 1990s, based largely on the subject of what started as a black hole argument, is essentially the following: that for the short-ranged Hamiltonians, if the system is gapped, then the ground state has area law of the entanglement entropy. So what this tells you in particular is that if you look at 1D, right, in 1D, the entanglement entropy should be proportional to the area. Well, what is the area? Just 2 endpoints, which means it's a 0-dimensional system, which means it's a constant. Now, because it's a constant, what this tells you by our argument is that in order to describe the S, which is a constant, you need to keep a constant number of states. And that's why in practice, something like 100, or in harder cases, maybe 1,000 of states is enough for DMRG to describe one-dimensional system. Now you will see why we get into problem once we hit 2 dimensions, because in 2 dimensions, this, according to what we just said, goes as the first power of L. And herein lies the problem, because that means that now, in order to describe a thermodynamic system in 2 dimensions, I need to keep 2 to the power L, well, infinite number of states, as L goes to infinity. I'm the only person standing between you and the drinks, by the way, right? I've just realized, which is a rather uncomfortable realization. So So let
May just ask a question?
yeah, I think this is a great idea for me to stop talking and let you ask questions. Yes.
To prolongate the time for drinks, essentially. No, I mean, I'm just wondering, so this is the entanglement entropy.
Yes.
Okay? How do you get the entanglement entropy? I mean, it's essentially you cut a d-dimensional system into
Yep.
two parts.
Exactly.
So naturally, the interface between the two of them is d minus one dimensional.
Exactly.
So it's just the entropy of the interface. What, I mean,
Right.
this in principle is what you would expect be the systems entangled or not. So what is
What's so special about the area law? Right. Exactly. So it turns out that if you were to take an arbitrary random eigenstate of a short-ranged Hamiltonian, right? So take Hamiltonian, pick any state. It would fail, by the way, if you have exactly solvable problem. But let's just say not a special case, but generic random eigenstates. You will find that the entropy, the entanglement entropy, does not actually grow proportional to the boundary between A and B. It actually grows as the volume of A or volume of B, respectively. So, and in fact, it does it with probability 1, which means almost certainly. Well, what I mean by this, you know what statisticians means when they say almost, right? It's not the same as what politicians mean by that, right? So, so the statement that if I were to place a number over here, I will almost certainly hit a rational number, right? That means that that statement is true with probability 1, except you could say, wait a second, but what if you place your finger here and this is a pi over 4? Well, clearly not a rational number. That's why the prefix almost. So the statement is that essentially the measure, so if you imagine that this unit length is entire measure of entanglement entropies of my system, then most of them, basically of measure that's the entire size of the Hilbert space, will have volume law. And there will be only a set of states of measure 0 in this sense, which means with probability that's negligible, that would actually have the area law. And the most, surprising in a sense, the fact is precisely that for the gapped Hamiltonian, this actually works. Yeah, so that's the non-trivial part about this. Now notice I underlined the word gapped. If you did the same for the gapless systems, that is a subject for another discussion. The gapless systems in one dimensions have to be described by a conformal field theory, that there is some deep connection to the 1 + 1 dimensional physics. And there is a Cardi-Calabrese formula that tells you that if the system were gapless, instead of a constant, you would actually get a log of the system size, right? So to me, precisely, if you had a gapless 1D system, then this would actually go as something proportional to the central charge, for those of you who know about CFT, times the log of the system size. Question, yes, at the back. Pardon me? Right, so in a gapless 2D, depends if you're dealing with bosons or fermions. So for the bosonic two-dimensional system, up to now the consensus is that it doesn't care. It still goes as the area law for the ground state. For the fermionic system, it turns out that instead of L, this becomes L times log of L plus weaker powers of L. Right, so at most you generally pick up an extra log if you're dealing with the gapless systems. But my point is that if you can't solve a gap system in 2D, then yeah, don't ask me about gapless. That's just pointless. That means it's hopeless. By the way, Lucille Savary, who's going to be here next week, is going to talk in detail about the quantum spin liquid. And I realized that I kind of left a hook dangling, but I didn't quite tell you about what the ground state of the triangular lattice actually is. Do you want to know, or shall we go for drinks? All right, I'll sketch it very quickly. All right, so remember I said J2 over J1 over here. So it turns out that up to about this, you get a 120-degree state. If you were to enlarge this number to about 15%, so G2 is 15% of G1, you will end up with so-called stripe state. The stripe state is just, it's something that looks like where the top spins are all pointing up, and these spins are all pointing down, and the next row are all pointing up, like that. Now, in between is what's known or believed to be a quantum spin liquid, and that's going to be the subject of Lucille's, the entire set of lectures. All right, well, I'll be around, so ask me questions